Hello everyone. Welcome to this session on achieving FPGA timing closure. My name is Sukrut. I work as a senior application engineer at Lattice Semiconductor. I specialize in FPGA software tools enablement, and I provide customer support as a timing expert. I have over 9 years of semiconductor experience with a master's degree in electrical engineering from San Jose State University, and I've been with Lattice since the last 5 years. I'm also a key contributor to Lattice's internal and external training contents for software tools. Today in this session, we'll look at some of the FPGA timing closure techniques that includes lattice gradient constraints methodology, synthesis guidelines for timing closure, map and par timing closure techniques, and understanding the timing reports. FPGA timing closure techniques. One question you might always ask is, what is an STA? An STA stands for static timing analysis. It is a process of validating the timing performance of a design by checking all possible timing violations. In our FPGA design software tools, we have static timing analysis engine or tools that are used to analyze the design's timing performance by seeing if we met the timing or if we failed timing for a particular design. Now you might ask, what is timing closure? A timing closure is a process by which an FPGA or an ASIC design is modified to meet its timing requirements. If you talk to any FPGA timing engineers, they might always say that my design has to run at 250 megahertz, my design has to run at 200 megahertz. In order to meet this 200 or 250 megahertz, we have to do some modifications in the designs and also use FPGA software tools. This entire process is called as the timing closure. Most of these modifications are usually handled by the tools based on the constraints provided by the designers. Why do you think timing closure is a challenge? Oftentimes these days, there's a huge increase in the device density and the size of the designs. If you look at Lattice A1, it's a 500K LUT device compared to our Crosslink NX, which is a 40K LUT device. Comparing the designs in these two devices, it might be a little easier to meet timing on a Crosslink NX design compared to an A1 design because the device density on an A1 is too high. And the size of designs can also be too high. Also, in an FPGA, we have hardened blocks like DSPs and EBRs that are placed in specific locations where routing can be too problematic in a complex design. Sometimes, designers might use poor placement seed, which also results in design not meeting timing. Designers who don't understand the device architecture might underutilize the device, making it another challenge for timing closure. Sometimes, the design's clock speed and interface speeds are too high to make it more challenging to meet timing closure. Understanding the cause of the timing failure is very important to meet timing closure. Let's start with RTL coding. RTL coding is the most crucial and effective area to achieve timing closure. We always say that instead of simply coding the design to meet the functionality, you can always instantiate embedded blocks or do pipelining techniques or retiming techniques as the best approach to meet timing closure. Using software. Sometimes misunderstanding and misusing the software options like strategy options and switches can lead to timing failure. Oftentimes, wrong timing constraints provided during map and par also lead to timing failures. Sometimes the designers might under-constrain the design or over-constrain the design, which also leads to timing failures. It's very important for the designer to understand the hardware before coding an RTL. If the architecture and other characteristics of the target device is not completely understood, the device might not be fully utilized or might be misused, and this can cause timing failures. The designers should make sure that they don't overestimate the performance or overlook specific features of your target device to meet timing. Area balance. You've often heard of the statement like, parallelism is not always true, even though it is faster. Why do we say this is, if you're increasing parallel processes is faster, but sometimes it consumes a lot of additional resources, which may lead to large implementations. This may push certain non-critical paths to become critical, causing timing failures. So parallelism means having parallel processes. If you have a parallel processes, functionally, this might give you a better results, but when you implement a design, it might cause a lot of area, it might increase the resource utilization, causing an area abundance, and then this might lead to timing failure. Resource utilization is another important factor to consider. You always should make sure that the device that you chose is not overly utilized. Our FPGA software tools cannot honor all the timing constraints when the resource utilization of the device is exceeded. In this case, the user will have to recode the RTL or either have to move to a larger device to meet the required specifications. Here's a sample Radeon timing flow. In a typical Radeon timing flow, users would input timing constraints and design entry to synthesis. Once you perform synthesis, it is recommended to run timing analysis. Once you run timing analysis on the post-synthesis design database, if you look at the timing reports and see there are timing failures, then you will also have to go back to your RTL to see if there's anything that you can do to fix those timing violations. Our timing report usually tells you if the failing path is a logic-intensive path, or if the failing path is because of the placement and routing. At the post-synthesis stage, the design is still not placed and routed, so all the placement and routing data will be an estimated value. Hence, if it is a logic-intensive failure, then users can always go back to your RTL and fix the timing violations. Once all the timing violations are fixed, go run map on the design. In the map stage, users can input a post-synthesis timing constraints file and run map timing analysis. Once you run map timing analysis, if you have timing failures, these timing failures could either be due to your post-synthesis timing constraints or because of the RTL. So again, look at the failing path and see if the failing path is because of the large logic delay or if the failing path is because of the large routing delay. If it's the logic delay, then go back to your RTL and fix your RTL. Also, look at timing constraints. If you have applied improper timing constraints, it might lead to timing failure. At this stage, if you see a large routing delay, then probably the running par might fix those issues because this is still an estimated timing. Once you see no timing violations, run par on the design. Once you run par, run that final timing analysis. In this stage, if you see timing violations, and if the failing path has a large logic delay, then this has to do with the RTL. If it is not the logical delay and if it is a routing delay, look at the timing constraints provided. In certain cases, users might also have to do floor planning to reach timing and close timing of this design. Once you close timing, run bitgen and validate the design on the hardware. Some of the recommended steps to resolve timing issues. Always make sure that you use effective and appropriate timing constraints for synthesis, map, and par. Timing constraints are very crucial to achieve timing closure. In this example here, we have included clock constraints, input-output delay constraints, and timing exception constraints. Often, clock domain crossing paths are sometimes ignored. So make sure you apply proper timing exception constraints to asynchronous clock domains and make sure that you get the proper timing closure by using appropriate timing constraints. It is always recommended to run an initial timing flow with synthesis, map, par, and par timing. You will get an understanding on where the timing failure actually occurs in your design. Here's the latest Radeon constraints methodology. In this constraints methodology, if you look at on the left-hand side, this is the logical domain. On the right-hand side is the physical domain. In the logical domain, users include HDL files, IP and IP constraints, user constraints in the form of an LDC or SDC as an input to synthesis. This user constraints can be input using a pre-synthesis timing constraint editor or by manually entering the constraints. Once these are provided to synthesis engine, we run a process called a constraints propagation engine. This constraints propagation engine will only be executed if there's an IP in the design. Once constraints propagation engine is executed, this constraints propagation engine is used to provide an effective constraints between the IP constraints and the user constraints, and it also resolves any conflicting constraints between these two. Once CPE is executed, it goes to synthesis. Based on the synthesis engine chosen, LSE or Simplify Pro, a post-syn is performed after synthesis, and a post-synthesis UDB is generated. This post-synthesis UDB is a unified database file that includes the netlist, along with the timing constraints provided during pre-synthesis. At this stage, users can run a post-synthesis timing analysis, and the tool generates a .tws file, which is a timing report file, a post-synthesis timing report file. This is useful to understand if the timing failure that you see in the design might be because of a logic delay or because of the estimated routing delay. Once a post-synthesis UDB is generated, and if you are satisfied with the timing results, run map on this design. In the map stage, users can input more additional timing constraints or can also include physical constraints. These constraints can be input using the form of a PDC file. A PDC stands for a physical design constraint file. The physical design constraint file can include timing constraints and also physical constraints. We have a tool called Post-Synthesis Timing Constraint Editor, which allows users to create timing constraints from the GUI. Users can also include manual constraint. Users can also enter constraints manually using a source editor. We have a tool called Device Constraint Editor, which is used to input physical constraints, or users can choose manual way to enter the constraints. All this input goes to map stage. Once map is completed, map generates a map.udb file, which includes the netlist, physical netlist, along with the timing constraints from the pre-synthesis stage and the post-synthesis stage. At this stage, users can run a map timing analysis. Once the timing analysis is completed, map generates a .tw1 file. This is a map timing analysis file. This again gives a good understanding to the users if there's a timing violation, if it's because of the logical domain, or if it's because of the post-synthesis timing constraints added, or if it's because of the estimated routing delay. If it's because of the estimated routing delay, continue to run par, and at par, it might fix all the timing violations because of the estimated routing delay, or it might cause more timing violations. Par generates a par.udb file, which is a par which includes the physical final netlist along with the timing constraints that were added during the previous stages. At this stage, users can run a post-par timing analysis. This is a sign-off timing analysis where it generates a .twr file. This is a final timing report file which includes the proper logical delays along with the proper routing delays. At this stage, routing delays are not estimated, but these are the actual delays. In this case, if you see a timing failure due to a routing path, then you might want to do floor planning and go back to your map and path. Once you're satisfied with the results, you can generate the bit stream and then validate the performance on the hardware. In Lattice Radiant, we use SDC constraints, and these SDC constraints are used for timing-driven synthesis and place and route. In Lattice, Simplify Pro and LSE, which is the Lattice synthesis engine, both are timing driven. In the backend flow, our place and route engine is also timing driven. Some of the key factors to consider to drive these design timing closures include maximizing the timing driven when synthesis option is set to timing. If users are using LSE, which is the Lattice synthesis engine, always make sure the strategy option is set to timing. If you're using Simplify Pro, make sure that you uncheck the area in the strategy options. Our place and route engine is always timing driven. For users to input or create timing constraints or edit timing constraints, Radiant provides a timing constraint editor. This timing constraint editor can be used during pre-synthesis and also during post-synthesis. A pre-synthesis timing constraint editor is used to provide or create constraints for synthesis. A post-synthesis timing constraint editor is used to provide or create constraints for your post-synthesis, including map and par processes. Along with that, users are also provided with source editor to create constraints in the form of .ldc file that can be used by LSE tool, a .sdc file that can be used by both LSE and Simplify Pro, and a .pdc file that is used for map and par. In certain cases, the timing tool also generates auto-extracted constraints for whenever a PLL and an oscillator is used. These auto-extracted constraints can also be seen in the post-synthesis timing constraint file and are also written in the UDB file or the Unified Database file. As mentioned, the STC constraints can be used by both LSE and Simplify Pro, and in Radiant, the STC constraints used are based on the STC version 2.0. LDC, which is the lattice proprietary constraints file, is supported by Lattice Synthesis Engine and also supports some other physical constraints. These physical constraints are also in the form of an STC file. Some of the constraints that are covered in Radiant STC are clocks. These are used to define clock constraints, uncertainties, and latencies. These constraints include create underscore clock constraints, create underscore generated underscore clock constraint, set underscore clock underscore latency constraint, set underscore clock underscore uncertainty constraint, set underscore clock underscore group constraint. Along with the clock constraints, users can also set input or output delays to your IOs using the set underscore input underscore delay, set underscore output underscore delay constraints. Along with these constraints, STC also includes timing exception constraints that includes set false path, set max delay, set min delay, and set multi-cycle path. Now let us look at some of the constraining design guidelines. If you look at this image on the top, this is an FPGA boundary, and there are two registers in this. At the FPGA boundaries, users must include the input and output delay constraints for your input ports and output ports. Inside the FPGA, users have to declare all the clock constraints in order to achieve 100% timing constraints. To go deeper into this, clocks usually constrain all the paths to and from the registers or sequential elements. So constraints for clock include create clock and create generated clock. Make sure all the clocks in the FPGA are constrained. Along with the clock constraints, users should make sure all the input I/O ports are constrained using the input delay constraints at the top level. This input delay constraints can be constrained using the set input delay constraint. Along with that, all the output ports must be constrained using the output delay constraints. When these three sets of constraints are included, all the paths in the FPGA are constrained properly. Along with these constraints, users can also include clock latency constraint to define the relationship of top-level clocks that comes from an external source. This constraint can be in the form of set clock latency constraint. Along with defining the relationship at the top-level ports, users can also include uncertainty constraint to take jitter into account or put additional constraint on your clock period. This uncertainty can be added using set underscore clock underscore uncertainty on the respective clock. Along with these clock constraints, Radiant allows timing exception constraint to identify special conditions for the timing engine. And these constraints include false path. If you want the timing engine to ignore any paths, then use false path. Multi-cycle path allows the users to specify a certain path to be a multi-cycle path. Max delay is used to constrain two registers to make it place close by. Min delay constraint and max Q constraints. All these are timing exception constraints and are handled by Radiant. Please note, false path and multi-cycle paths along with max Q cannot constrain the paths on their own. This should always be associated with the clock constraint. This goes back to saying, make sure that all clocks in the FPGA are constrained properly. Now let's look at some of the synthesis guidelines for timing closure. Always use the timing-driven mode for synthesis. When you use a timing-driven mode for synthesis, the pros of this is it gives you better performance, meaning you might meet the required timing goal. But the con of this is it increases resources. There's always a trade-off between performance versus area. If you want to improve performance, you might have to give up on area. And if you want to improve area, you might have to give up on performance. It's very hard to meet the balance. Increased resources always negatively or might always negatively impact the performance of the design. Make sure there are proper, sufficient, and appropriate timing constraints applied to the design. It is very essential to provide the clock frequency and clock period and constrain all the clocks in the design. If you have any CDC paths and if you have multiple clocks, ensure that all clocks are constrained properly, and also the clocks between the interclock domains are constrained properly by either defining false path or by following proper CDC techniques by using synchronizers. Sometimes over-constraining the design at synthesis level can give you good results. You can reduce the target Fmax to the actual value post-synthesis. Radiant allows providing a pre-synthesis constraint and a post-synthesis timing constraints. So one of the best ways to do it is, if you're trying to achieve 250 megahertz, make sure that you put 300 megahertz for synthesis. In that way, synthesis can put more effort in meeting that 300 megahertz, and you can always relax it to 250 megahertz, which is a target frequency post-synthesis. But you need to keep this in mind that when you're over-constraining the design, there's always chances that you're increasing the resource utilization. It is recommended to run post-synthesis timing analysis. As I mentioned in the past, post-synthesis timing analysis will help in estimating the performance of the design. It can help you understand if your failing path is because of the logic or because of the estimated routing. If this is because of the logic, it saves you a lot of time by predicting the failure before running map and par. On more complex designs, it takes a long time to run map and par, and thus identifying the timing failure at the synthesis stage will save you a lot of time. Also note that post-synthesis STA and post-map STA only provides estimated routing values. Users must always run place and route timing analysis for timing sign-off. One of the most important things to achieve timing closure is the RTL coding. You need to always create RTL code by understanding the device architecture instead of just trying to meet the functionality of the required design. In this case, in this example, make sure that you use the output register of an EBR whenever possible to meet timing. If you look at this coding structure, when a user creates a code this way, the tool would automatically infer an EBR for this particular code. Instead of an RTL code this way, users can also instantiate the respective primitive to achieve the same functionality. If you look at this code, when you run map on this, in this case, we have a block RAM that is used. And if you look at the VM file, which is the post-synthesis netlist file, you will see that there is an output register used in this case. Why do I emphasize on using output register? Let's look at the next slide. In this case, if you look at this table here, always using primitives or making sure that the tool infers the right primitive is a key to improve the Fmax. In this block RAM example, if a user has a 9 width of an EBR and a 4096 depth of an EBR, and if they have used an output register, the tool would infer 1 RAM and look at the C2 out delay of this particular primitive. This is just 335 picoseconds. In case you use a width of 10, 2 RAMs are used, but again, in this output register case, the C2 out delay would just be 335 picoseconds. But if you have not used the output register, the same primitive would give you a C2 out delay of 1333 picoseconds. This increases the C2 out delay, thus having a long path or a critical path. If you look at more examples here, a 4096 into 10, the same thing, if you have not used the output register, than 1333 picoseconds, which is quite large of a C2 out delay. If you want to use two RAMs in a cascaded mode, and if you are using a registered output, this still results in 335 picoseconds. If you have not used an output register in a cascaded mode, it again increases it to 1333 picoseconds. This means enabling output register whenever possible reduces the C2 out delay by about 1 nanoseconds. Similarly, in this example of a DSP block, if you use an 18x18 DSP block in a signed mode with an output register, you will see that the C2 out delay of this particular primitive is only 210 picoseconds. But if you have used the same primitive without the output register, the C2 out delay increases by 1457 picoseconds. In more examples, if you use 19x19 and if you use an output register, it is 2669 picoseconds, and the number of DSPs use this for. Sometimes using primitives might not always improve the timing, but whenever possible, you should always make sure that you use the output registers to reduce the C2 out delay. Some more synthesis guidelines for timing closure. Whenever possible, using I/O registers helps in improved timing. Using I/O registers significantly improves timing when the interface timing is very critical. This improves the input setup time and clock to out timing by tuning the use of I/O registers. The I/O logic has a way to include these registers into the I/O logic, which will be placed in the I/O logic close to the boundary so that this meets the interface timing much better than placing those registers inside the fabric. In order for users to use the I/O registers, you can use the synthesis attribute synthesis syn underscore use IOFF is equal to 1. This guides the synthesis tool to place a certain registers into the IOs. In LSE, if you want to use this option, you can use the synthesis strategy option, use IO register. It is usually by default set to auto. You can make it to true or false based on the requirement. Now let's look at some of the par timing closure techniques. Always perform par with default strategy to gather more information. Run par multiple times with multiple iterations. Radiant allows you to run multiple iterations with different placement seed. Every time you run an iteration, it takes in a different placement seed, and therefore the results might vary. A new seed equals to a new placement start point. And for Nexus devices, we use an algorithm called simulated annealing. So simulated annealing, what it happens is it chooses a placement start point and tries to place the logic around that. So if you use a new placement seed, this placement start point might change and might help you meet the required timing. In many cases, floor planning the design can often help in timing closure. Floor planning can be done using Lattice Physical Designer in Radiant to manually floor plan the logic which is failing timing. For more information on how to use the floor planning, you refer to Radiant help. You can also check for the reports to see if there are any timing failures. You can examine the reports and analyze timing information. In this example, the par report actually suggests that there is a timing failure. If you look at this design, there's a worst slack of negative 7.961 and a worst hold slack of negative 2.766, indicating that the design has failed timing. Furthermore, users can check the timing report to see where the failing paths occur and what the failing paths are. You can always refer to timing reports and see where the timing failure is happening. In this example here, we have the source clock and the destination clock to be a different asynchronous clocks. In this case, users have to ensure that they're using a proper constraints like a false path constraints between these two to eliminate the tool to time this invalid timing violation. If this is a synchronous timing violation, then use certain CDC techniques to close timing. Here are some of the par strategy options that affect timing. The ones marked in red does not affect timing, but the ones marked in blue affects timing. If you look at the disable hold auto hold time correction option, which is always unticked by default. The auto hold time correction kicks in only when the setup violations are completely fixed. The tool tries hard to meet the hold violation. If the setup violations are not fixed, the hold time violation correction will not occur. Users can always disable timing driven by checking on this value here. If this is unchecked, and this is unchecked by default, our power engine is timing driven by default. You can also play with path-based placement options, change the placement iteration start point to choose a different placement seed, and you can run multiple placement iterations. And this multiple placement iterations ensures that there are different seeds chosen at different iterations. As you can see, this number goes from 0 to 100, and there are 100 placement seeds to try. And you can also choose an option to prioritize hold correction over setup performance. So if you have a setup performance of 200 megahertz to meet, and if you want the tool to prioritize hold correction instead of setup performance, then you can choose this option. You can also set the speed grade for hold optimization and also set the speed grade for setup optimization. The speed grade by default includes the target device speed grade for setup and an M speed grade for hold. And you can always ask the tool to stop once the timing is met. Understanding timing reports is very key and crucial to achieve timing closure. Here's a radiant timing report post-par, and here's a table of contents for this timing report. In section 1.1, we talk about design checking, includes the STC timing constraints that are provided by the user. Constraints coverage, we'll talk about what is the constraints coverage in the particular design. Overall summary, unconstrained reports, and if there are any combinational loops in the design. Section 2 talks about setup at multiple speed grades, which is the first time here we choose the speed grade 1, which is performing at corner at 85 degrees Celsius. This will give you a clock report, endpoint slack, and a detailed report. Section 3 will do timing analysis for setup at a 0 degrees Celsius. And again, here we talk about clock summary, endpoint slacks, and detailed reports. Section 4 talks about hold at speed grade M. In this, we see that the setup is performed at this user speed grade at two different temperatures, at 85 degrees Celsius and a 0 degrees Celsius. And the hold is always performed at an M speed grade at 0 degrees Celsius. An M speed grade is a virtual speed grade, which is the faster than the fastest available speed grade. The idea is if you meet hold timing at the M speed grade, you will meet timing on the other speed grades. Taking a deeper look at each of these sections, and section 1, we have 1.1, which talks about the STC constraints. These are the STC constraints either provided by the user or auto-extracted by the tools. This provides all the information about all the constraints that have made through in this part. Section 1.2 talks about the constraints coverage. Constraints coverage in this case is 100% because we've constrained all the clocks, all the I/O ports. The overall summary gives you a summary for a different speed grades. Overall summary provides the setup at multiple temperatures, which is at 85 degrees and 0 degrees, and hold at 0 degrees. This tells you if there are any timing violations in each of these corners. We also have a section which talks about unconstrained start and endpoints. If you look at this section and if you see some unconstrained start and timing start points, which means that these registers are clocked, but the endpoints are not constrained. If you see some of the paths listed here, you will either have to go and see if there are any clock or false path constraints that are missing. Another section also says there are clocked but unconstrained timing endpoints. In this case, if you see some of the registers listed in this case, this means that the endpoints are either not false pathed or if they don't have any clock constraints listed. Another section, 1.4.2, talks about start and endpoints without timing constraints. If any timing constraints are missed by the user, it appears in this case here. In this example here, we have 10 start or endpoints that are missing timing constraints. If you see some unconstrained input and output ports here, user can set the input-output delay constraints to make sure that these parts are removed from here and are properly constrained. In Radiant timing report, we also provide a detail on if some of the nets have missed clock constraints. In this example here, there are 2 nets that have missed timing constraints. So if you look at this report and if you see some nets listed here, go back and put those timing constraints so that you meet the 100% timing constraints coverage. Let's look at the next section, which is the clock summary section. This shows both the clock and clock domain crossings. At the beginning of this report, we report the clock constraint. The clock constraint here in this example is create_clock -name ref clock I with a period of 37 nanoseconds, and the port that is constrained to is ref clock I. The next thing after the constraint is the single clock domain constraint definition. In this section, if you look at this talks about the clock period, which is the 37 nanoseconds, which converts to a 27 megahertz clock, and also talks about what is the actual frequency that this particular clock can go to based on the I/O chosen. This particular target clock can actually go up to 167 megahertz, but the user has constrained it to 27 megahertz. There's also an MPW factor that is added to this clock. MPW is a minimum pulse width. Every component in the FPGA has a minimum pulse width. This MPW is limited by the I/O type of this particular clock, and that is why this is limited to 200 megahertz. The next section of this particular clock summary talks about any clock domain crossing paths. In this example here, we have multiple clocks, and this shows that there are no clock domain crossings for this particular clock along with the other clocks. List of endpoints and slack. This is a summary which lists all the endpoints of slack based on the worst slack first. In this example, the worst slack here is a negative 14.18 nanoseconds, and it lists the top 10 worst slacks in the descending order, with the worst slack first. You can always change this option to list more number of paths in the strategy options. In this case, there are 76 paths that are failing timing, but only 10 paths are missed. Go to the strategy options to increase the number of paths so you can see all 76 of them. Detailed timing report. The detailed timing report provides a detailed report of a particular path in question. In this example, you look at the path begin. This is a path's detailed report summary section. In this, the path begin includes the first register, which ends with a Q pin. Path end is a DF pin. So this is a register-to-register timing path, going from a slice R5 C60D to a slice R5 C56C. The source clock and the destination clock says the first register is clocked by a source clock pixel. The second destination register is clocked by a destination clock underscore pixel. This is a single clock domain crossing path. In this case, this path has 8 levels of logic, and it has a delay ratio of 55% of routing delay versus 45% of logic delay. If you remember my previous conversation, if you run a post-synthesis timing report, and if you see a large logic percentage here, which means that this path has a huge logic intensive path, and the routing delay is 55%. In this example, it's only 55% of routing delay, and this path has fast timing. If there are any clock skews, that are also listed in the clock skew section. And the setup constraint provides the setup constraint that you provided in the constraints file. Here's a detailed report. The next section of the detailed report includes the source clock path. The source clock path includes where the clock is originating from. In this case, this clock is originating from the clock OS pin of the PLL output pin, and the cell or site name is PLL_core_PLL_ULC. This gives the users a very good understanding on where this PLL is placed. This PLL in this example is placed in the upper left corner. Once after this clock OS, this clock goes to the clock pixel, which is the instance that is clocked at, with a net delay of 2.909 nanoseconds. This makes it the arrival time to be a 2.909 for this particular clock path. This section talks about the fan out. This clock pixel or the clock OS has 4264 fan outs or loads. Here's the data path. In this data path, if you look at this path goes from the first register and goes all the way up to the destination register. There are multiple things to consider here. The first column gives you the name of the net. The second column gives you the name of the site. The third column gives you the delay name. The fourth column is the increment. And the fifth column is the arrival or required time. The sixth column talks about the fan out. Certain things to look at in this case is if this particular delay is either a register delay or a net delay or a CTO delay, or we have C1 to FCO delay. Each of these delays are different. Reg delay is a sequential element delay. The CTOF delay is a combination element delay. The C1 to FCO delay is the CCU to component delay. This is an arithmetic path, and the individual component delays are listed along with these register delays. These individual component delays are then added up totally with the incremental delay to give you the total delay. Users should also pay attention to the fan out section in the timing report. If there's a huge fan out, which means that it undergoes a large logic levels. So reducing the fan out can help you meet timing. And reducing the number of logic levels also helps in improving the timing. This is the destination clock path. In this destination clock path, you see that the clock that is clocking the destination register is the same clock as the source clock. This goes from a CLK OS, and this PLL is placed at the PLL ULC, which is the upper left corner, and goes to the clock pixel, which is clocking the destination register. Along with that, the timing report also says if there are any clock latency constraint added to this particular clock, and it gives you a net delay of 2.909. This 6.734, which is listed here, is the constraint value. So this particular clock is constrained at 6.734 nanoseconds. And there's a 1 fan out. And this clock pixel has a 4,264 fan outs. Along with all of this calculation gives you a 2.146 positive slack, which means that this clock has clear timing. If you look at this table here, this gives you a slack calculation. The arrival time includes the source clock delay plus the data path delay, which is 2.909 plus 4.634, giving it a 7.543 of arrival time. All of this is in nanoseconds. And the required time is the constraint plus the clock net delay minus the setup time. In this case, it is 6.734 plus 2.909 minus 0.046, which gives you a 9.68489. This setup time is the setup time of the component of the destination register. In this case, the setup time of the destination register is a negative 0.046, which means this is helping us by giving us a good positive value. Therefore, the slack or a setup slack here is required time minus the arrival time. The required time is 9.689 minus the arrival time, which is the 7.543, giving rise to a positive slack of 2.146. Some of the things to consider after you read the timing report is looking at the unconstrained start or endpoints in the timing report. When you look at the unconstrained start or endpoints, you will see that some of the clocks might be missing timing. So when you see that some of the clocks are missing, go back to your map report and check the number of clocks. Map report gives a good understanding of how many clocks are used in the design, what is the driver, and what constraints can be added. Once you look at them, go back to your SDC or a PDC file and constrain them to get the 100% timing coverage. Along with that, You can also look at the list of unconstrained IOs in the timing report. Once you look at the unconstrained IOs, always add the missing input and output delay constraints to achieve that 100% timing 100% timing coverage. Here are some reference documents that were used in today's session. Lattice Radiant Timing Constraint Methodology User Guide. This guide gives you a complete understanding of different constraints that are used and also when to use and how to use. We have multi-corner timing analysis for Nexus devices. This is an application note. By default, until now, we did not have multi-corner timing analysis for Nexus devices. But in Radiant 2023.2 release in December, we will have this multi-corner timing analysis for Nexus devices. But if users want to understand how this multi-corner timing analysis can be done manually, you can always refer to this application note, FPGA AN 02063. Along with that, we also have Lattice Insights, which is a training portal for everybody to understand and to learn about Lattice tools. This can be accessed using www.latticesemi-insights.com. Along with that, users can also refer to Radiant Help, which gives you good understanding of all the tools that are supported in Lattice Radiant software. Coming to the summary section, today we talked about how to read timing report, which helps in understanding the cause of the timing failure. Always look at the delay ratio and logic levels in the timing reports. If the logic delay in the timing failed path is more, follow synthesis guidelines for timing closure that are mentioned in the slides. If the routing delay in the failed path is more, then follow synthesis guidelines for timing closure again. If the logic levels are high, try to reduce the logic levels of the failed path. If nothing works, then try to do floor planning. Make sure that the design is 100% constraints covered. We talked about 3 sets of constraints that are needed to achieve 100% constraints coverage. One is the clock constraint, to constrain all the clocks in the design. The I/O constraints used to constrain the input ports and the output ports. The combination of all of this will lead to 100% constraints coverage. Over-constraining the design may help in synthesis, but may increase resource utilization. But it's worth a try. Manual floor planning must always be considered as a last resort to close timing. Sometimes floor planning is too complex that it might not help you much, but you should always consider this to be a last resort to close timing. All right, here we go. There are some questions coming up in the Q&A widget. I want to start with the first question. Besides setup and hold timing violations, what are the minimum pulse width violations that are included in the timing report? I repeat the question. Besides setup and hold timing violations, what are the minimum pulse width violations that are included in the timing report? That's a very good question. Our Lattice Radiant timing reports includes the MPW information, which is the minimum pulse width information, which means that every component in the FPGA runs at a particular timing, and this MPW report gives an understanding to the user if that particular component has met its timing or if it is exceeding timing. MPW typically checks against the single point, such as if the pulse width of the clock signal is more than the required value, or if the I/O port is clocked faster than the defined value. If a memory block is running faster, or the max rates of the data sheet can also be seen in the MPW. Another question that came in is, why is hold time not dependent on the clock frequency? This is another good question. Unlike setup time checks, the hold time check is done only at the same edge, making sure that the data captured and the current data are not the old data. So this is why the hold time is not dependent on the FPGA clock frequency. And when we look at the FPGA performance, timing performance, we only look at the setup time and not the hold time. Another question that came in is, are false path and set clock groups the same thing? Ideally, they are the same thing, but both commands actually tell the tool that, hey, don't time this particular path or don't time this particular paths. When user uses a set false path, they get more flexibility to set certain paths to be a false path along with the clocks. But when you use a set clock groups, this is essentially telling the timing tool that there are certain clock groups. Don't time any timing paths that goes between these two clocks. You can achieve the same thing with set false path, by using a from path and a to path, but you will have to include clocks in this. If you are including a set false path from clock A to clock B, this means all timing paths that are clocked between clock A and clock B are set as false path. You can achieve the same thing using the set clock groups by using set clock groups dash clock A and dash clock B. So all the paths between clock A and clock B and clock B and clock A will be set as false paths. I see more questions coming in, but in the essence of time, we're going to have to end the session soon. So if all these questions, we'll get back to you on the answers after the session. Thank you so much for being a part of this FPGA timing closure techniques. Thank you.